the chapter 27 on circuits. So far, what we talked about was resistors in series that have the same current, and equivalent resistance is sum of all the resistances. And resistors in parallel that have the same voltage, the resistance, equivalent resistance, follows the inverse law, as you see. And talk about the Kirchhoff law. We had junction rule that says for any junction, sum of the currents coming into the junction is the same as sum of the currents going out of the junction. And we had a loop rule that says if you take any loop in the circuit, sum of delta V equal to 0. And in order to account for these potential differences, we have some other rules that say passing through a battery. If you go from negative to positive side of the battery, delta V is equal to positive voltage of the battery. And going from positive to negative side of the battery, delta V is equal to negative voltage of the battery. And if you're passing through a resistor that has current I in it, then if you go in the direction of current I, then delta V is negative IR. In the direction of current, delta V is negative because you're going from high potential to low potential, because current goes from high potential to low potential. And then going against current, delta V will be positive IR. So this was so far what we had. And I have two examples here. You see a lot of resistors and a lot of batteries. It says each resistor is 4 ohms and each battery is 10 volt. Find the current in the resistor that's labeled R, this resistor. Do you also see my cursors?
Yes.
Yes. Yes. Okay. Thank you. Yes. This is the resistor we want the current of in this circuit. Any ideas? It seems to be very complicated, but it is not actually that complicated.
Just use loop rule?
Yeah. Yes. How do we do that?
I guess just focus in a box that has the resistor in it, like make it just focus on that.
You mean this this one?
Yes.
If you write the loop rule, for example, in that, then it requires knowing all the currents going through the other two resistors, but we don't know that. You see, because you don't know the current through any of the other resistors, it is best if you can write down an equation that does not involve any other currents. Is it possible to do that? You need to stare at this figure for a while in order to actually come up with a good idea. You see, as I said, you need to make a circuit and apply loop rule so that you don't have any other currents involved. So let's avoid all the other resistors. So if I go this way, I avoid this resistor, and then I avoid this resistors. I go through the battery, it's good. It's one V here, another V here, and then I go here, another V here, and then I go this way, and I don't have any other currents involved. Because when you go through a resistor, then you have to multiply the resistance by the current through that resistor to get the voltage. But if you don't go through any other resistor, then you don't need that. So if you go this way, so 10 volt, 10 volt, 10 volt, and then negative 10 volt. So you have 20 volts of potential minus IR equal to 0. Again, we're going from here as 10 volts plus 10 plus 10 minus 10 minus IR back to where I started equal to 0. So therefore 20 volts should be equal to IR. 20 minus IR equal to 0, and R is 4 ohm. So the current I will be equal to 20 over R, which is divided by 4, 5. Is that clear? Anyone?
Yes.
Okay, very good. Any questions on this?
So with loop rule, it doesn't really matter like what path you take as long as it all adds together to make sure that it applies to the rule, correct?
That's right. Any path you take along one complete loop, closed loop, sum of all the potential differences should be 0. So that's what we did for this loop that you see. We could avoid all the other currents, all the other resistors, and we could write one equation that involves only the current through the resistor that we want, and we can solve for that.
Thank you.
You're welcome. All right, so let's go another similar problem is this. It says each one of these capacitors is 10 microfarad and each battery is 12 volt. Find the charge on the capacitor labeled C, this one. You see my drawings, right?
Yes.
Yeah.
Okay. So can you do a similar thing with this? Because now if you want to find the charge, if you want to write down an equation that involves the charge of this capacitor, you need to avoid all the other capacitors so that you don't have to write more equations for those capacitors' charges. Because when you write delta V is Q over C, right, for each one. So can you do that and try to do it and then let me know your result?
Yes, you can do that.
Mm-hmm. And what is the result? What is the charge of this capacitor?
I need to finish doing the calculation.
Mm-hmm.
Is it 1.2
1.2
times 10 to the negative 4 micro
yes, yes. So that's right, 10 to the negative 4 coulomb. 120 microcoulomb. All right. The way you do it, you start from somewhere here, and then you go in this route. So you avoid all the other. You get 12 volts here, or 1V, and then you go all this route so that you don't have any other thing, and then you come here. So you get 12 volts, and when you pass through this, you get negative Q over C, because that's the voltage of the capacitor. The charge on the capacitor divided by the capacitance. And that's equal to 0 according to Kirchhoff law. Okay, and then now because you have the capacitor, you can find the charge. So Q is equal to C times 12. C is 10 microfarad, so Q is equal to 10 microfarad. 12 volts. So that becomes 120 microcoulomb. Okay, or 1.2 times 10 to negative 4, as you said. The next part that I want to discuss in this chapter is RC circuits. RC circuit involves a capacitor, as you can see here, and a resistor and a battery in the circuit. And there's a switch. And if you close the switch, then the current will flow and the capacitor gets charged. And the question is, how does the charge of the capacitor changes with time? At the beginning, as we close the switch, the capacitor is uncharged. And then when we close the switch, the capacitor starts getting charged. But we want to see how the charge of the capacitor changes with time. So if I apply the loop rule for this circuit, as you see here, I can start from here and then go past the battery. I'll go from negative to positive. I write V, and then when I pass the capacitor, because this side will be positively charged, I get negative Q over C. And then that's the voltage of the capacitor. And then I pass through the resistor because I'm going in the direction of the current, which is downward in the resistor. So I write negative IR, and I come back to the same point in here. And therefore, I write equal to 0. That is loop rule for this circuit. And this is an equation that has Q in it and also has current in it. But the current and Q are related. The current is actually rate of change of Q in this case. And current as a function of time is the derivative of Q with respect to time. And I want to put that back in terms of I so that I get everything in terms of Q. So if I do that, will be B minus Q over C minus R times dQ over dt equal to 0. And this is an equation that involves a function Q and its derivative with respect to time. And now I need to solve this equation. This is called differential equation, and I want to solve this differential equation. So to make it look easy, simpler, I take away the time dependence because we know that Q is a function of time, and then I multiply by C for now to make it look like this, get rid of the denominator, and then I move this RC dQ dt to the other side. It becomes like this. The idea to solve this equation as a function of, for Q as a function of time is separation of variables. You need to separate the variable T and variable Q. So in order to do that, I write it this way. dt over RC, I put this side, CV minus Q, I put under dQ. So it becomes like this. And because this is Q, I want to take CV minus Q or negative of that as U. I can multiply by a negative sign, these two switch, and then this negative sign comes here, okay? And then after this, if you separate the variables, you need to take the integral of both sides. Then you take the integral of both sides, the integral of dt over RC on one side, the integral of dq over q minus CV on the other side. And you know that the integral of dt, this RC is all constant, comes out, and integral of dt is just t, and integral of du over u, if you take q minus CV as u, becomes ln of u, which is q minus CV. And there is also a constant of integration, which is, we call it P because usually we call it C, but because C is capacitor here, we call it P. P is the constant of integration, which we can determine by the initial conditions. So how do we find P? First of all, Q minus CV is negative, and then absolute value of Q minus CV is negative of Q minus CV, which is CV minus Q. So I'm going to replace this absolute value of Q minus CV with CV minus Q. So the equation looks like this. I get rid of the absolute value because I know that this Q minus CV is always negative. And then now I want to determine P. So initial condition is that when at the beginning, when we close the switch, the capacitor is uncharged. There's no charge on the capacitor. And therefore, we apply this condition. We said that T equal to 0 when we close the switch. charge is 0. So this is what we have. T is 0, we have Q equals 0. So I put these T equal to 0 and Q equal to 0 in this equation, and then find out what P should be. And then if I do that, I get 0 on this side, and if you put Q equal to 0, you get ln of CV plus P. So we get this equation. Therefore, P will be negative of ln of CV, and then if you put that back in the equation, you get negative T over RC, ln of CV minus Q, minus ln of CV, and you know ln minus ln means ln of the ratio. So negative T over RC equals to ln of CV minus Q over CV. And you can write it as 1 minus Q over CV. And then you can say that this e to the power of this quantity is equal to this quantity. Yeah. So 1 minus Q over CV equals to e to the negative T over RC. And then you can write, you move this one side, this another side, you get Q over CV equal to 1 minus e to the negative T over RC. Or Q equal to CV times 1 minus e to the negative RC. So this is our equation that you can find in the book. This is the derivation I presented. And this is for charging a capacitor. You notice that if T equals to 0, now e to the power 0 becomes 1, 1 minus 1 becomes 0, so Q starts from 0. And then if T goes to infinity, e to the negative infinity goes to 0, and then Q becomes CV. And in any time in between, Q is smaller than CV, as we mentioned. If you plot the Q versus time, it goes like this. Charge asymptotically increases and goes to this value of maximum, which is C times V. And if you want to find the current is dq over dt. You can find that too. If you take derivative, this is a constant, this is a constant. This gives us negative 1 over RC times this negative becomes positive CV over RC e to the negative T over RC. And so C cancels and V over R becomes initial value of the current. So current becomes initial value of the current, which is V over R, times e to the negative T over RC. So this is the current. And the current goes from initial value decaying to 0, and like exponential function. And then if we look at these quantities, like a time constant is called, this quantity RC is called time constant, and it is denoted by tau equals to RC. So this quantity is time constant. Time constant is actually the time for the charge to reach 63% of its maximum value CV. At this time, which call it tau, right now it is at, for this curve, it is at 2 milliseconds. This will be the time constant. And this is the time where the curve reaches 63% of its maximum. And also for the current, tau is the same, but it is the time it takes for current to drop to 37% of its initial value. And as you see again in here, this is 37% of its initial value. And it is again at 2 milliseconds. So this is charging a capacitor by a battery and R, because C and R are both in the circuit. We call it RC circuit. And then the same calculations apply to discharging a capacitor. For example, if now it switches here, the capacitor is charged, and then if you flip it over, it discharges through the resistor. If you do the same kind of calculation, you see that Q is equal to Q naught times e to the negative T over RC. and the current will be the same, I naught e to the negative t over RC. Similar calculation, I just didn't want to do that again. Very, very similar and a little simpler. All right, this is an example. Now, this is one of the questions of the book. It says that when the switch S is closed on A, there is a current I to resistance R. The plots give that current for 4 sets of values of R and capacitance C. R naught and C naught. The second one is 2 R naught and C naught. The third one is R naught and 2 C naught. And fourth one is 2 R naught and 2 C naught. It says which set goes with which. You need to match 1, 2, 3, 4 to A, B, C, D in this. Let me know if you have an idea how to do that.
For 2 and 4, would it connect to D and C since it's starting at a higher value compared to the singular R naught? And
That is a very good point, yes. Because if you have a higher resistance, the current starts at a smaller value, right?
yeah,
So A and B should be related to 2 and 4. That's a very good point. So what now? What exactly is which one?
Would 4 be B because it's going to be RC, since T is over RC, and 2R and 2C, it's going to be T over 4 RC, so it's more gradual.
That's right, that's right. You said for 4, we have a smaller current to begin with, but we have longer time constant. So it takes longer for the current to drop. That's correct. 4 is B. Yes. What else?
3 be D for the same reason.
3 is D, you said?
Yeah.
Yes, that's correct. 3 is D because it has this larger current, but it has also a larger time constant. So 3 is D, yes. And what are the next ones?
Would 1 be A and 2 be C?
The current starts at a higher value for 1. So 1 is either C or D. And D is taken, right?
Oh, sorry, I got those backwards. Would 1 be C and then 2 be A?
Yes. 1 is C and 2 is A. Is everybody clear on that? So you need to realize that the current to begin with, I naught, it's hard. I naught is V over R. So if you have a smaller resistance, I starts at a higher level. So 1 and 3 go with C and D. And then between these two, 3 has twice as long time constant as 1. So you see that D has longer time constant. It takes longer to drop. So 3 is D and 1 is C. And then the other two, which we have the 2R and 2R here, they start at the lower value, half of the other one. And 4 has a longer time constant. It means it takes longer to drop. So 4 is B. And 2 is A. This is another example of the book. It says the figure shows 3 sections of circuit that are to be connected in turn to same battery via switch. The resistors are all identical, as are the capacitors. Rank the sections according to the final charge on the capacitor, and B, the time required for the capacitor to reach 50% of its final charge, greatest first. So first, let's talk about part A. Which one has bigger final charge on the capacitor or equilibrium charge? Any ideas? The go back to the equation. Remember, U was CV times 1 minus e to the negative t over RC, right? So what determines the final charge? Final charge is when what? When t goes to infinity, right? Means that this exponential goes to 0, then Q equals CV. What do you think now? So remember, the batteries are all the same, capacitors are all the same, and Q final is CV. So what can you say about the final Qs?
They have the same charge.
Same charge, yes. Because you see, the resistance is here. It affects how fast the charge goes to maximum. But what determines what the maximum charge is just capacitor and voltage. And the voltage of all of them finally will be the same. Because as time goes to infinity, the currents drop to 0, and then there's no potential across the resistors. So the potential of the battery goes on the capacitors, right? So for part A, say all of them have the same final charge. So they're all the same. What about part B now? Which one has more time required for the capacitor to reach 50% of its final charge?
Would it be 1, since
1.
they're all in series? So you have the resistor, the capacitor, and then going through the resistor again.
That's right. The two resistors in one are in series, so they make larger equivalent resistance, and therefore the time constant, which is RC, is larger for that one. And then for the second one, they are in parallel, so they make a smaller resistance because, you know, it's R times R divided by R plus R, remember? So it becomes R squared divided by 2R becomes R over 2. In the first case of one, the resistance, equivalent resistance is 2R. In the second case, the equivalent resistance is R over 2. And then what about in the third one? So basically the battery sets up a current in that resistor that is connected directly to the battery. So that does not affect the RC part, right? So this one is connected directly to the battery, so it has a current in it. But how the current changes in this one, and how the current changes or the charge changes, depends on this resistor that is in series with it. So in this one, the time constant is decided by RC, which is this R. So basically this one has RC, time constant RC. This one has R over 2 times C. This one has 2 RC, the time constant. So in here, tau 2 RC. In here, tau is RC divided by 2. In here, only this one affects the problem. And so tau in this case is RC. So you see this one, 1 is the highest, 3 is the next, and 2 is the next. So 1 is greater than 3 greater than 10. In this case, we have a circuit like that. It's an ideal battery. And R1, R2, R3, R4, R5, R6. Here it says the current through R6 is 1.4 amps. And it is asking for the EMF of the battery, the ideal battery. Any ideas? So you need to work your way down from here, go all the way to find the the EMF of the battery or voltage of the battery. So let's see, what can you say about the voltage here? If you have the current and you know the resistance, what is the voltage across this R5 and R6? In order to go find the EMF of the battery, you need to know the currents through these two resistors. Because if you apply loop rule, then you get E minus IR equal to 0. And then you need to have the I's, right? You need to have the currents. In order to find the currents, then you need to find the current of this one and the voltages and all of that. So here, we see what information we can get from these values that we have. Can we replace these two by their equivalent? We can say, all right, this is 4, this is 8. We can replace them by an equivalent of 12, right? Because they are in series. So if you have 12 ohms here, and here, you have 12 ohms, and the current is 1.4, we can find the potential difference here across this 12 ohm resistor, which is the same as potential difference across R4 because they are parallel. So the potential difference across R5 and R6, R5, 6, equal to 12 ohm times 1.4 amps. Is what? If you multiply 1.4 by 12, yes, you get 16.8, right? That's 16.8 volts. That's also equal to V4. Now you can find the current in 4. I4 equal to V4 over R4. R4 is 16, right? So 16.8, 16.8 divided by 16. That's about 1.05, I guess. And now here you see that 1.4 amps goes here, and 1.05 goes here. Therefore, you can find the current through this one. So you can say I2 equal to I4 plus I5, 6, or which is the same as I6. How much is that? 1.05 amp plus 1.4 amp. So it becomes 2.45 amp. Right? So this becomes 0.45 amp. And then you can find the potential difference across R2. So V2 equal to R2, I2. How much is V2 now? 2.45 times 2 ohms, right? R2 is 2 ohms and the current is 2.45. So 2 ohm times 2.45. Sorry for my bad writing here. It's hard to write on the computer. That's 4.9, right? 4.9 volts. So that's V2. And then we had V4. What was V4? V4 was 16.8. And now V2 is, you see, from here to here is 4.9. And this voltage is 16.8. So the sum of these two voltages becomes voltage across R3. So the V3 becomes 16.8 volt plus. So V3 is what? 16 and 5 is 21.7, right? Volts. That's V3. Now we can find I3. What is I3? I3 is V3 over R3. R3 is 2 ohm, so it becomes 21.7 divided by 2, which is 10.85 amps. So the current through I3 is 10.5 amp, 10.85 amps. And here was 2.45. So I have it here. And then now we can find the current through I1, R1. So I1 becomes the sum of those two, 10.85 plus 2.45. So I1 is, that's 15 to this becomes 11, 13.3. So I1 is 13.3 amps. And what is V1? V1 is I1 R1, which is 13.3 times 2. So V1 is 26.6. All right. And V3 was what? V3
1.7.
V3 was 21.7, yes. 21.7. So if you apply the loop rule for the battery in this, you see that V minus 26.6 minus 21.7 equals to 0. So the V of the battery or EMF is equal to 26.6 volts plus 21.7. Okay. Which is 47.8, 48 points, no, 48.3. And that's the answer. So you see, you work your way down from this, you find the voltage, which is the voltage of that. Then you can find the current, you find current of the R2, and then you find the potential difference of R2, you add V4, you get V3, you can find current in 3, and so forth. You find the current in R, voltage in R, and then add the voltages. So quite a process. This is another example we can work on. We have about 10 minutes. The resistance R1 is 1 ohm, R2 is 2 ohm, and the ideal batteries have E1 2 volts, E2 and E3 4 volts. What are the size and the direction up or down of current in battery 1, size and the direction of the current in battery 2, and size and direction of the current in battery 3? What is the potential difference VA minus VB? All right, so here you see, first of all, you could reduce this circuit in here, R1 and R1. These two are both have the same current, so they are in series. So you can put 2 R1 in here. Let me see if I can write. No, I cannot write here. So 2 R1 in here, and here also 2 R1, because these two are in series. This R1 and this R1, and then R2 is 2 ohm. So all the resistances are the same. This is 2 ohm. Some of these two that are in series also 2 this is also 2 ohms. All right, so we can reduce this, and E1 is 2 volts, E3 and E2 and E3 are 4 volts. So if I go back to this empty page here, I can draw that in here. So we have 2 ohm here, 2 ohm here, and we have 2 volts in here, and 2 ohm here, and here also we have a battery. Sorry, and here, so V1, which is 2 volts, 2, and V3 that are 4. So V1, 2 volts, V3, V2, sorry, V2 and V3, 4 volts, and R is 2. All of them are. So R is 2. We want to see the current through each part first, basically. The answer we want, it's asking for the current through each battery. So basically, we can say the one current is going here, let's call it I1, and one current going here, and it calls I3, going with V3, and this one going down here, we call it I2. So as you see, if you look at this junction, you get I3 plus I1 equal to I2. So I3 plus I1 plus I2, that's one equation. And then you can write a loop rule starting from here, let's say V1, because you're going in the direction of the current here, get negative RI, RI1, and then we're going in the direction of the current again here, negative RI2, right, minus V2, 0. So this V1 was 2, so this is 2 minus 2I1 minus 2I2 minus 4. So 2 minus 4 is negative 2, and and move these over, 2I1 minus 2I2, or plus 2I2. So I1 plus I2 is negative 1 amp. Right? So far we know I1 plus I2 is negative 1 amp. We need one more equation. So if you go back, you see that if you look at the this loop, you see V3 minus IR minus V2, which is 0, which is the same. See, V2 and V3 are the same. So it's 4 volts minus this IR minus this IR minus 4 is equal to 0, right? So minus I3R minus I3, and the resistances are the same. So we have negative R I3, negative R I2 equal to 0. So that means that R can be cancelled. So it means this I2, I3 plus I2 also 0. So it means I3 is equal to negative I2. Right. This is another equation. I can put that in here. So instead of I3, I can put negative I2. And then so from the equation, I will get I1 negative I2 equals to I2, or I1 is equal to 2I2. And then if I put all of these in, this one in here, 2I2 plus I2 negative 1. So I2 negative 1/3. And I3 is 1/3 of an amp. And I1 is negative 2/3. Oh, sorry, negative 2/3. That's right, negative 1 times 2/3 of an amp. So this means that you see that I2 and I1 are negative, means that the direction that we chose in the circuit were wrong. So it means if you go back, I1 and I2 are both negative, and R3 is 1/3. So basically, this one was the other direction. I2 was also in the other direction. And these are the values.